You know, from the battery that cranks your car engine to a bolt of lightning that just rips across the sky, our entire world is powered by this invisible force. But what is it really? Well, today we're going to connect the dots. We're going from a simple battery all the way to a massive spark. Let's jump right in.
Okay, let's kick things off with a little puzzle. You've got two batteries here, one for a car, one for a motorcycle. And look, they're both 12-volt batteries, so what gives? Why can one of these things start a huge car engine and the other one just can't? It doesn't seem to make sense, right? Well, stick around because by the time we're done here, you are going to know exactly why.
To crack that battery mystery, we've got to go all the way back to the basics. So Section 1 is all about the energy between charges, that fundamental push and pull that pretty much governs the entire electrical world.
So it really all boils down to one thing: work. Think about it. If you try to push two positive charges together, they're going to fight you, right? They naturally repel each other. All that effort you're putting in, all that pushing, it doesn't just disappear. It gets stored up as potential energy. Now flip that. What about opposite charges? Well, they want to get together. The system basically does the work for you, and when it does, it releases all that stored energy.
Okay, for our second section, we get to the real heart of the matter. What is voltage? I mean, this whole idea of stored energy is great, but it kind of depends on the specific charge you're messing with. What if we could make a kind of universal energy map for any spot in an electric field? Turns out, we can.
First, let's just nail down potential energy. Physicists usually label it with a capital U. The best way to think about it is like a specific boulder sitting on a hill. The potential energy it has depends on its own weight and how high up it is. It's a property that's tied directly to that specific boulder.
But electric potential, what we all call voltage, this is something else entirely. And honestly, this is the real game changer. Voltage isn't about the specific boulder you're using. No, it's about the height of the hill itself. You get it? It's the amount of potential energy available for every single little unit of charge. It basically creates this energy landscape. It's a property of a specific spot in space that tells you exactly how much of a kick any charge would get if you dropped it right there.
All right, now we've got the concepts we need. So let's bring it all back to that question from the beginning. Section 3, voltage versus energy. It is officially time to solve the battery mystery.
And here is the single most important thing to remember. Voltage is not the same thing as energy. Not at all. Voltage is the potential for energy that each little bit of charge has. It's the push, not the total shove.
And this explains everything perfectly. Yeah, both batteries have that 12-volt potential difference. That just means every little packet of charge, we call it a coulomb, gets the same 12 joules worth of energy push. But the car battery, it's like a giant water tank. It can hold and move a ton more charge. We're talking 60,000 coulombs, compared to just 5,000 for the motorcycle battery.
And so when you actually do the math, you take that voltage push and multiply it by the total amount of charge you're shoving, the difference is just, whoa, it's staggering. That car battery can deliver 720,000 joules of energy. That is 12 times more than a little motorcycle battery. See? It was never about the strength of the push per charge. It's all about how much stuff you can push with it. And just like that, mystery solved.
So we've seen how voltage works on a scale we can understand, like with batteries. But now let's zoom in, and I mean way in. Section 4, the world of electrons. Let's see what happens when we apply these exact same ideas to a single, unbelievably tiny particle.
The thing is, joules are just a massive unit of energy when you're talking about individual particles. It's overkill. So scientists came up with a much handier unit, the electron volt, or EV for short. And it is exactly what it sounds like. It's that teensy tiny bit of energy that one single electron picks up when it gets pushed by 1 volt of potential.
And this is precisely how old-school gadgets like this vacuum tube used to work. You'd set up a voltage difference between two metal plates. An electron chilling out at the negative plate is just loaded with potential energy. The second it's let go, it's pushed away by the negative side and yanked toward the positive side, instantly converting all that stored-up potential energy into pure kinetic energy, pure speed.
And what happens is it's absolutely mind-blowing. An electron's mass is so tiny it's almost nothing. So even a pretty modest 100-volt push, it rockets that thing from a dead stop to nearly 6 million meters per second. Let me put that in perspective for you. That's over 13 million miles per hour. All of that from a simple voltage difference. It's incredible.
Okay, so we've tied voltage to energy. For our last section, we're going to bring it all home and connect all the dots. Section 5, fields, voltage, and sparks. We're about to see how our voltage map relates to the actual force that gets everything moving in the first place.
You know, that hill analogy we've been using? It is honestly the best way to get this. So voltage is like the height of the hill. It's just potential. The charge is like the boulder itself. So what makes the boulder actually start rolling? Well, it's the steepness of the hill, right? In the world of electricity, that steepness has a name, the electric field. That's what tells you the direction and the strength of the force.
And if you look at this diagram here of the two parallel plates, you can see it perfectly. Those electric field lines, the little arrows, they're always pointing away from the high voltage plate and toward the low voltage plate. They are literally showing you which way is downhill on that energy landscape.
And the relationship between them all is just beautifully simple. The total voltage difference is just the strength of that electric field multiplied by the distance it covers. And that means you can get a high voltage in two ways. You can have a ridiculously strong field over a short distance, or you can have a weaker field that stretches across a much, much longer distance. And, you know, this has some seriously dramatic real-world consequences. So, let's say you want to make a spark jump across just 1 single inch of dry air. How much voltage do you think you need? You need to build up a potential difference of 75,000 volts. That is a huge number. And what you're doing is creating an electric field that is so powerful, it literally rips electrons right off of the air molecules, turning the air itself into a temporary wire. That's what a spark is.
Okay, so that leaves us with one final massive thought to chew on. We all know lightning is just a ginormous spark, right? And we just learned that voltage depends on two things, the strength of the field and the distance. So think about it for a second. Does a storm cloud that's way up high produce a more powerful lightning strike than one that's closer to the ground? Well, you've got all the tools you need now to figure that one out.